All right, let me start off up here. I want to start with a little bit of quantum optics, which some of you are experts on, and you can go to sleep. First thing is, I almost always like to work in the Heisenberg representation, not the Schrödinger representation. So operators change, states don't. Second thing is we all know the harmonic oscillator. We have these A's and A daggers. The annihilation operators and the creation operators. And there's a special state for them called often the vacuum state, which is the state that's annihilated by the annihilation operator. Now, let's say that we have some dynamics. And the dynamics is such that at the end of the dynamics, we have these annihilation and the creation operators, D and B dagger, which of course obey the same commutation relationships. But B is equal to alpha A plus beta A dagger. In other words, it mixes up the annihilation and creation operators. First thing is, if I plug in this commutation relationship for B and B dagger, I find that alpha squared minus beta squared is equal to 1. Okay? This, of course, tells us that I could have, whoops, that's absolute value of beta. This, of course, tells you that I could have chosen alpha and beta to be represented by cosh of R and sinh of R. Now, if my state started off as A times little a equals little a times A, then the expectation value of A, capital A with little a is equal to just little a. So this is the so-called coherent state. You send in a signal. You now ask, what's the expectation value of B? And the expectation value of B then becomes basically alpha squared plus, my memory is just failing me. In this state A is, I believe, alpha times A. That's not right. Pardon?
Alpha A plus beta A star.
It's alpha A plus. Oh, come on.
But you have to look at
Anyway,
A dagger, which is like
yes, I know. It goes to the left, and so that gives me an A star. And
so that's why when you look at B being alpha A plus beta A star, you, as operators, you get alpha A plus beta.
sorry, you're
alpha
right.
little a
Alpha A plus
beta A star.
beta A star. Yes. Now, if alpha and beta are real, Koch and Cinch, and A is real, then that's going to amplify it. This goes as e to the r times A. If A is imaginary, then it de-amplifies it. So this acts as a so-called phase-sensitive amplifier, which means that one of the phases of the signal that you send in gets bigger, the other phase gets smaller. This also introduces noise. In other words, if one looks at, for example, the expectation value, well, let me just put the vacuum state in here. B dagger B, which is the number of B particles in this A vacuum state. This looks like alpha. Squared. My memory's going on me these days. This has got to be real. It's alpha squared plus beta squared, I believe. And so we get extra noise. However, as I mentioned before, this guy is phase sensitive, so it makes some things bigger and some things smaller. The other guy I want to look at is if I now have two different A's, an A tilde, and I do B is equal to alpha A plus beta A tilde dagger, and B tilde is alpha tilde A tilde plus beta tilde times A dagger. This is called a two-mode squeeze state, or a two-mode squeezing. And in this case, if again I take A is equal to A, and I feed that into the system, then I find that B, expectation value of B, is basically, oh, I didn't want to do that right now. First thing is if I do the commutation relationships on these guys, I get that alpha squared plus minus beta squared, just as before, equals 1. Alpha tilde squared minus beta tilde squared equals 1, and beta over alpha equals beta tilde over alpha. So they have the same phase, and since that's sinh and that's cosh, that also tells us that they have the same amplification and the same phases for both of those things. And this is called a two-mode squeeze state. Now, this thing, the amplification in this case is the same for all phases. So no matter what phase you send in there, no matter what the phase of A is, you get exactly the same amplification coming out of the B port. So this is an amplifier. So these guys behave somewhat differently. But once again, this system produces noise. So anytime you have this mixture of A's and A daggers, you get extra noise thrown into the system. Incidentally, there's a neat little model of an amplifier that one can build, which also teaches us other things. Let me take a Lagrangian. So this is a Lagrangian of two fields, psi and phi. Psi travels along the x-axis. Phi travels along the y-axis. At x equals y equals 0, so we get a delta function there, delta x, delta y. Some coefficient times q dot. Let's take q dot squared, so that's just a free particle. And then we have a coupling between phi there's no epsilon in there. Epsilon times d by dt phi times q plus mu times dt phi at t and 0, and this is again at t and 0. So this oscillator has, or this free particle is coupled to both of these fields. Now, an important part here is that this has got a negative Lagrangian, negative kinetic energy. And the first reaction of most particle physicists or whatever would say, that's unstable. It's horrible. The answer is it's not. As long as mu squared is smaller than epsilon squared, this is perfectly stable. And in fact, this produces an amplifier where these A's are the annihilation operators for the psi field at two different frequencies. And the the A's are the annihilation operators for the psi field, and the A dagger and the A tildes are the annihilation operators for the phi field. If one looks at this thing and one looks at the amplification, as a function of frequency, it looks like this should be the log of the amplification versus the log of the frequency, where this drops at 6 dB per octave. And this knee frequency depends on the difference between epsilon squared and mu squared. Now, those of you that have built amplifiers or whatever, and you look up in your data book for what these amplifiers look like, what does the amplification look like? That curve is exactly what you see in the data handbooks. So basically, the phi represents stuff that comes from the power bar, where you have a maximum energy, and everything tries to build its way back up to the maximum energy. The A tilde is the annihilation operator, which increases the energy up to its vacuum state, which is the maximum energy state instead of the minimum energy state. Many particle physics papers that you read, they get all hot and bothered if they see a negative Lagrangian. And assuming the couplings are right, there's nothing to be afraid of. They also try to identify the annihilation operator with the lowering operator. But obviously, for the phi field, the annihilation operator is a raising operator. It lifts you from a negative energy to a less negative energy.
That roll-off
Pardon?
the roll-off curve that was just erased for an amplifier is more or less what you have for a completely classical operational amplifier. Is it for quite different reasons?
I didn't quite get that. My hearing.
Just erased your curve.
Yes.
Of an amplifier.
Yes.
Well, that's what you get for a completely classical operational amplifier. Same curve,
Well, I mean, everything is quantum.
if you like.
So basically, if you analyze that amplifier quantum mechanically, you get exactly this same thing.
Okay.
And what the transistor does is produce this mixing between the annihilation and creation operators on the various output arms.
Okay. I think you can get it without using H-bar.
Yes, you can get it without using H-bar is certainly correct. But you can also get it using H-bar.
Okay.
And these annihilation operators and creation operators obviously have H-bars. So what I wanted to do was to emphasize as a quantum system, it's really easy. And I mean, one of the nice things about quantum linear systems is they're the same as the classical. You just have to interpret certain things in a slightly different way. Where am I? So what I want to do now in this paper is to discuss, how do I do this? Yes. Is to argue that LIGO is quantum using these ideas. Now, what I mean by this is not that LIGO detects quantum gravity, but all of the things inside LIGO, and in particular those bloody big 40-kilogram mirrors, are quantum. And that it has been demonstrated that those are quantum already. Now we know that ever since quantum mechanics got invented, there have been all of these arguments as to whether or not there are some limits to quantum mechanics. this was, actually I'm going to take this off. Niels Bohr didn't help things by emphasizing the difference between measuring apparatuses, which are supposed to be classical, and quantum systems, which you're making measurements of. That are these tiny little things. So all of these arguments tended to produce a whole series of arguments that have gone on now for almost 100 years as to whether or not there are some limits somewhere with quantum mechanics, and that whether or not quantum mechanics somehow or other disappears at some scale or another and produces classical physics for more energetic things. And that's the sense in which I want to discuss in the rest. Let me remind you of LIGO. LIGO is the laser interferometer gravitational wave. I keep calling them gravity waves, but that term got stolen by the fluid mechanics people 100 years before, only about 50 years before Einstein. But anyway, I will probably keep calling them gravity waves. It's huge. 4 kilometers long, light bouncing back and forth in the arms of about 1 megawatt is the flux of energy traveling back and forth between those two mirrors. About 20 to 40 watts coming into the thing, and this is Fabry-Perot cavity, which has a high Q factor, and it amplifies that incoming radiation up to this 1 megawatt bouncing back and forth inside the system. We have 2 end mirrors over here, and we have a laser interferometer, and the location of those end mirrors is very carefully designed so that almost all of the radiation that bounces back and forth and escapes back comes back out of this port. A tiny fraction, about 1/1000th of the radiation, goes back out of this, what is called the dark port. So this laser interferometer is adjusted so that it's almost at the null. Not quite, and that extra little radiation coming out of this arm is very important. The way in which that is tuned is that there's a secondary system set up here with a capacitor. There's a capacitive coupling between it and this mirror, and they can put a very small electric charge on it to adjust the length of the arms to, about somewhere between a nanometer and a picometer. So it's an incredibly large system. These mirrors and the half-silvered mirror over here, of course, they don't use silver. It's a dielectric beam splitter that are sitting here. They all weigh about 40 to 50 kilograms. So they're definitely macroscopic devices. And this is the noise. I'm sure most of you have seen this. This is a noise graph of the interferometer. And this blue stuff here is the latest run that's just finished. And this purple curve here is the calculation of the quantum nature of light. And there are 2 things in that quantum nature of light. We notice that we have a more or less straight line over here. Sorry? So the x-axis is frequency from about 10 hertz up to about 1 kilohertz. And the vertical axis is, if you will, the noise intensity, but they've translated it into sensitivity of the interferometer to motions of the mirror And these go from about 10 to the minus 20 to 10 to the minus 17. This red curve here is due to seismic noise. Notice it falls off incredibly rapidly, and it to some extent hides this purple part of the curve. This part of the curve is due to so-called shot noise. Namely, you've got a photodetector, that little bit of light, about 20 milliwatts of light, coming out of the dark port, which is what you measure. Of course, you're measuring it by photodetectors, and that's going to give you Poisson noise, square root of n. And this is the impact of that square root of n noise on your ability to detect gravity waves. This part of the curve is called the radiation part of the curve. And what it does, what it's due to is that the light, the 1 megawatt light inside the cavity pushes on the mirror. And it also has shot noise in it. Much more shot noise, and it pushes the mirror back and forth. Now, pushing those mirrors back and forth, of course, produces noise that you don't want to see. And this part of the curve is due to that. So the noise budget is very, very accurately determined by all of the calculations that they've done, including all of these parts of the rate curve. So the light wave, even though it's a 1 megawatt light wave, is definitely acting like a quantum source. But that's not the question we want to look at. The question is whether those mirrors are quantum. Those 40 kilogram mirrors are quantum. So let me build a much simplified model of this whole system. The laser interferometer, because it's looking out the dark port, is sensitive to differential motion of those two mirrors, of the order of 10 to the minus 21 meters. They're 4 kilometers long, and you're measuring their length to within 10 to the minus 21 meters. So what's important is this differential motion. The common motion tends to get rejected. It just bounces back out of the input port, and you never look at it. So to make it simple, let's get rid of that common mode and have a system which only has a differential mode. Namely, in this case, we have a beam splitter here. We have two fixed mirrors here. They're glued to the Earth. Well, not to the Earth because of all the seismic problems, but anyway, they're completely fixed. And they bounce off a central mirror here, which can move back and forth. Now, clearly, when it moves in this direction, it shortens one of the arms and it lengthens the other arm. So what happens when that mirror moves is it changes the phase of the light hitting it. The light comes in on from these two different directions, hits it, and each of them gets their phase shifted. One of them gets a positive shift in the phase, and the other one gets a negative shift in the phase. Furthermore, this beam splitter is designed in such a way that light which comes in from this port has the same, 1 over the root 2 of the amplitude of the light coming in, and 1 over root 2 of the light coming in going up that arm. So they have both positive amplitudes or negative amplitudes going back and forth to the mirror. Any light that came in this port got distributed as with a plus sign in that direction, but a minus sign in that direction. The mirror is a unitary device, and so the two orthogonal modes coming in here or coming in here get distributed into two orthogonal modes, namely plus and plus, or plus and minus, which are orthogonal to each other, going up those two branches. So this just describes the beam splitter, how that beam splitter works and divides the light coming from the various directions into 1 over square root of 2 of the amplitude, because you want the square of the amplitude, which is proportional to the energy, to be half going in one direction and half going in the other direction. But it picks up an extra minus sign. And similarly, on the way coming back, the common mode, the stuff coming in from the left gets split plus and plus, and the stuff coming in from the top gets distributed as plus and minus going this way. So that means that the light coming in from this direction, once it comes back, and if the interferometer is set up exactly on its null port, gets split up, comes back out of this port once again. Any light coming in this direction, again, goes back out that port. Now, we're going to displace things a little bit, so a little bit of the radiation comes into that minus port. Comes into that came into the bright port, goes back out of the dark port. What happens at the mirror? Well, the mirror is just a boundary condition, right? The mirror reflects the light in such a way, and I'm assuming here, and it doesn't matter what the assumption is, basically, the light comes in here and as 0 at the mirror. The boundary condition at the mirror is that the field is equal to 0. But of course, if this has been displaced, it also picks up a phase which is proportional to twice the amount that this mirror has moved, and minus twice that, a phase of twice the distance that the mirror has moved from the other side. So the sign of this phase shift has opposite signs on these two output ports. Incidentally, this term in here, number 1 is that I have made the assumption that z squared is tiny and I can neglect it. So this is only the lowest order in z here. What about the mirror motion? Well, the mirror is just a free particle, mass times the time derivative of z. This mass is 40 kilograms, let us say, is equal to the force on the mirror, A times the pressure, the area times the pressure, exerted by the light on the mirror. And that pressure is proportional to this is basically the energy density is proportional to the energy density falling onto that mirror. Now, this is quadratic. I don't want to solve quadratic equations. But the light hitting it is a megawatt, and I can regard that as a coherent state with a megawatt of classical radiation hitting that mirror, plus tiny fluctuations induced either due to the annihilation and creation operators of the light field or due to the motion of the mirror due to gravity waves coming by and so forth. After the light goes through, comes out the dark port, it falls onto a photodiode in order to measure what the amplitude or the number of photons coming out there is. And the photodiode current is proportional to basically the flux of photons. Basically the flux of photons, which is the negative frequency part, which has the creation operators in it, and the positive frequency part with derivatives of the y direction, since it's coming out in the y direction, coming in there in order to give the photon flux current. The input I'm assuming to be a coherent state. In other words, there's a classical part, which is proportional to alpha, and then these quantum operators which measure the quantum, these are the annihilation operators of the electromagnetic field. In the bright port, it's this classical field coming in plus these annihilation operators. But of course, most of this gets reflected back out the bright port again, and you never see it. Coming in the dark port, you just get the annihilation operators, plus the Hermitian conjugate, of course, which are the creation operators. Now, I played a little trick here. In other words, these are at frequencies that are not exactly the same as the frequency that you're sending into the interferometer. And I'm measuring that difference as nu. So omega is the frequency of the light, 10 to the 15 hertz of the order of. And nu is the difference between that frequency and the frequency that I'm looking at here in each of these cases. Notice that whether nu is positive or negative, this is an annihilation operator because its actual frequency is omega plus nu. These nus are going to be of the order of 0 hertz to kilohertz, which is much, much, much smaller than the 10 to the 15th hertz in omega. Well, one now can go through all of the mathematics in order to solve these equations. So this is the reflected wave. It has this term in here. L is the length of the interferometer, which you tune to be 0. Z is the location of that mirror, and you stick a very small 0 point on that so that the two legs of the interferometer aren't exactly the same length, and so a little bit of it goes out the dark port. Since Z is assumed to be extremely small, nanometers, compared to the 4 kilometers of the system, and compared to the wavelength of the light, 1 over omega. So this is a very small factor, and we can linearize with respect to it. And so we finally find what the output of the Y port is, of the dark port is, looks like this. It has one term in there which depends on the displacement of the mirror, and another term which depends on the annihilation and creation operators that came into the dark port. There's a tiny little factor which refers to the annihilation and creation operators that came into the bright port, but they're suppressed by the same amount as this term which suppresses the light, the coherent light that came in, and a little bit leaked out of that port. So one of the first things to know about LIGO is all of the noise doesn't come in with the laser, it comes into the dark port. This was something that was first stated by Carl Caves in 1980. The group around Kip Thorne was working on the noise in laser interferometers, as was I. I had gotten interested in it at that time as well. Now, this factor of B in that formula comes about because of the reflection of the radiation off the mirror. And that came and comes right back the port that it came in, namely the dark port. So this is due to the noise due to the direct reflection. Z is due to the noise caused by the motion of the mirror. So and this term turns out to be responsible for the shot noise. This term, of course, the mirror gets moved around because of the radiation pressure acting on it from the laser. And so there's a noise source in here, which again comes from only the B's, the B annihilation and creation operators. The A stuff comes symmetrically and hits the mirror, and they just cancel out. They put exactly the same pressure on the mirror. The B coming in one direction had a minus sign stuck into it because of the beam splitter. And so it has opposite effects on the two sides of the mirror and push the mirror around. So the amazing thing is that all of the noise that affects the accuracy of the interferometer comes in the dark port. Well, almost all. Factor of 1,000 difference between them. The force on the mirror turns out to be proportional to B sub nu. That's the annihilation operator for the field plus a nu distance above the frequency omega, plus B dagger of minus nu. That's the dagger of the field that comes in with frequency omega, little omega minus nu. This is all the stuff that has that same frequency of e to the I nu t. Because it's quadratic comes in there, the e to the I omega t's cancel out between the annihilation and between the positive and negative frequency terms, so they drop out. And the only forces down around kilohertz frequency comes from these B's. So now there are two noise sources. If we look at the motion of the mirror is m times the second derivative of the position of the mirror is equal to this force, which means that the motion of the mirror in frequency space goes as the area divided by the mass times the frequency squared. So the amount of noise that comes from the radiation pressure on the mirror drops as the frequency squared of the signal that one is looking at. That was why in that original diagram, at low frequencies, you got the radiation pressure noise, which fell off. And at high frequencies, you got the shot noise, which came from that B term that I mentioned before. So the total noise in the interferometer has two terms in it. One is that shot noise term, and the other one is this radiation pressure term. Here's again the radiation, signal detection, the photon number, and written in terms of these various fields, the flux of photons, which you're going to measure with your photomultiplier. And there will be two terms. One is proportional to alpha squared times sine, and the other one is proportional to B times alpha times sine. So if you collect all these terms together, one gets that running into the photomultiplier, the annihilation operators, the thing associated with e to the minus I nu t, that are going to be detected by the photomultiplier, has a form that looks like this. Oops, I erased it. That's exactly the form of an amplifier or of a two-mode squeeze state. So this whole system acts like an amplifier for the noise coming in, and in particular, it produces noise. It basically amplifies the quantum fluctuations of the signal coming in, both at frequency nu above the central frequency and frequency minus nu below the central frequency. You get excess noise produced by this guy. And those are all the things that come into, it's this noise source plus its complex conjugate that affect the noise coming into the photomultipliers. So the outgoing flux will be that of a two-mode squeeze state, squeezing between the modes with plus nu and minus nu. This just refers to that. And we noticed in that original curve that the radiation pressure noise and the shot noise are approximately equal in about the 50 to 100 hertz regime. And this is exactly the place where both of those, the squeeze noise has its usual minimum. Now, how can I get rid of it? Well, one way I can get rid of this noise is instead of using the vacuum state that corresponds to the B coming in other words, making sure I've got nothing coming into the interferometer from that port, I send noise into the interferometer. What do I mean by that? I send in a squeeze state such that after it's gone through the whole system, it leaves me with the vacuum state for this linear combination of the B's. Then the noise, then this annihilation operator here will be in its vacuum state, which will be much less noise than it would be if one had one of these squeeze states coming in. And so the first thing that one can do is one can get rid of the noise by feeding a squeeze state into that dark port, a two-mode squeeze state into that dark port. That will reduce the noise to a vacuum noise. In fact, I can then continue and also feed in a squeezing of that, a one-mode squeezing. Each of the B sub nu and the B sub minus nu, I can squeeze those furthermore in such a way that I can reduce the noise even more by feeding noise into the dark port. Now that sounds completely counterintuitive, that how in the world do you get rid of noise by feeding noise into the system? Well, quantum mechanically we know that if we feed it in with the opposite phase, they can cancel each other. And a couple of years ago, the people at Ligo ran one of their first tests of this. They built a little small interferometer to test out these ideas. And instead of feeding in just the vacuum into the dark port, they feed squeeze states in. Here is, this curve here is, this one here is what you would expect to get, is that it? Sorry, this curve is what you would expect to get. Then if they went and fed in that squeezed noise, you could get this curve here. And this squeezes the light in a different phase as you go along in frequency. So each phase has a different squeezing parameter on it. Now, the particular squeezing that they chose was such that it actually increased the shot noise. That's not necessary. If you do it properly, you can decrease the shot noise at the same time as you decrease the radiation pressure noise. And we notice down here at around 50 hertz, one has in fact reduced the noise even further.
What is the ordinate there? What is the number?
Pardon?
The y-axis, what is it?
The y-axis is just some log of the displacement. Well, this one is not. Yeah, it's basically the log of the noise. So this is just a measure of how much noise you're getting out. And you've noticed that you've drastically decreased the noise. You've increased the noise in the shot noise, but you've decreased the noise here in the radiation pressure area and in the shot noise area at the same time. Doing it properly, you can actually decrease both of them and have a curve that looks something like this. Now this was something that I suggested that they could do almost exactly 40 years ago. It's nice in having an example, you know, all of these funding agencies and so forth look at the impact factor of magazines or impact factor of articles and so forth, and they go over a time period of about 3 years. This is something that was important 40 years in the future. Those impact factors are largely crap, even though everybody uses them because they're a number, and a number I understand. The physics in the paper I don't understand. Anyway. So what's happening here is that this feed in the input of that dark port is canceling with the noise that is generated by the system and reducing the noise drastically. In fact, this whole technique has now been implemented in all of the LIGO systems, the 3 LIGO systems and Virgo, in order to increase the sensitivity by a factor of about 3 to 4 all across the frequency band for their next run. Now, I promised talking about classical earlier. What would happen if the mirrors were classical? Well, the first thing one has to do is to ask, wait a minute, if they're classical, how does a classical mirror interact with a quantum field? The light field is quantum. How do they interact with each other? The mirror is classical, so it's not operators. It's just got values for all of its quantities. Well, one of the favorite systems is semi-classical physics, right? Semi-classical physics is that the gravitational field interacts with the expectation value of the quantum operators. But that's silly here, because the expectation value of all of these B's and B daggers, and remember that the noise coming out was linear, their expectation value is all 0. So in the expectation value, there's no noise. So that would say that the mirror introduces no noise whatsoever. If it were classical, well, that's obviously silly because we know, we've seen it, we've measured it. The mirror does introduce, the radiation pressure does introduce noise into the system. So you could say, well, that proves that the system is not semi-classical. All right. But I don't think anybody actually has ever taken semi-classical gravity seriously anyway. So what else could one do? Well, a former student of mine, Jonathan Oppenheim, has been spending the last 5 years or so, trying to explore whether or not one could have a quantum theory of matter and a classical theory of gravity. And so he spent a long time trying to understand this classical quantum interface, how one can produce a consistent theory of that. And part of the answer to that is that one makes the interaction stochastic. In other words, the quantum pushing on the classical matter, interacting with the classical matter, acts as if it were a stochastic field with the stochasticity introduced by the fluctuations in the quantum forces. So if one has a Gaussian or a coherent state that pushes on the mirror, what you have to do is to replace that quantum force, or these B's and B daggers, by classical C number fields, B's and B stars, where those B's and B stars are numbers. So one can try to do that, and then if one looks at what you get in the photomultiplier, you're going to get the radiation pressure noise is those terms that I had, which were B sub nu plus B dagger sub minus nu, become classical fields, but classical stochastic fields, which have the same, standard deviation, if you will, the same mean and the same standard deviation as the quantum fields do. So now the mirror actually could be pushed around and will be pushed around by this radiation pressure. The problem, of course, is that one can no longer feed in annihilation operators to cancel that, because these are simply classical random variables, and these operators are operators, and I can never cancel an operator with a number. Operators have an infinite number of numbers in them, and besides, these are stochastic. These B's are stochastic, and I've got no knowledge of what they are. I don't know what got fed in by this quantum noise. So this guy has got the same distribution as, they can't interfere with each other. So they both basically got the same distribution. I.e., this stochastic process, which as far as I know is the only type of theory which has a chance of interacting a classical system with a quantum system, doesn't work either. It can't produce the results like this. There's just no way it can happen. So what does that tell us? That tells us that those 40-kilogram mirrors, their center of mass motion is quantum. People have been pushing things up. They've interfered buckyballs with each other with, atomic mass of whatever it is, 1,000 or something. They've done interference patterns, so those certainly act like they're quantum. And people keep trying to push it up a little bit higher to see whether they can make other things which act quantum mechanically. Well, we already have one. Ligo with 40-kilogram mirrors. That's almost my weight. 40-kilogram mirrors which are acting quantum mechanically, in which one can see the difference between them behaving as a classical system and as a quantum system. Now, of course, they've implemented this. Of course, it's quantum, so there's something that's small. And the answer, of course, is that the motion of these mirrors introduced by this radiation pressure is small. It's about 10 to the minus 16 meters. The sensitivity of these systems is about 10 to the minus 21 strain sensitivity. And they're 4 kilometers long, so that gives you about a distance of motion of these quantum fluctuations that are about 10 to the minus 16 meters. But it's hard to sort of see that, this 40-kilogram object is acting quantum mechanically, yes, on these kinds of scales, but at that point it comes really hard to set up a theory which is only going to be, it's quantum when it's very tiny distances, but it's classical when it's bigger distances. So the room for creating a theory like that is, I think, pretty small by now. Now, if your theory acts in the same way as quantum theory does over short time scales, so that this mirror is able to transmit these fluctuation forces through the mirror and producing the phase shifts in the reflected light on the time scale over which it's acting like it's quantum, then this argument, of course, says nothing. But at least the lesson I take away from this is we now know things that are 40 kilograms in weight can, under the right circumstances, behave quantum mechanically. And if they don't behave quantum mechanically, usually that's because they're constantly interacting with their environment, and that, of course, destroys the quantum coherence that one expects from a quantum object. It effectively keeps measuring the quantum object, and that's why it's not behaving properly. That's why it's not behaving quantum mechanically, usually. But LIGO has put in a huge amount of effort to make their mirrors behave as close, removing all other sources of decoherence, damping, etc., from those systems so that they really do behave quantum mechanically. Thank you. Yes.
Time for a quick question. There was another experiment done at Ligo a couple of years ago in which a group from MIT and Caltech put the mirror into the quantum ground state to demonstrate the quantum nature of it. Do you know anything about that?
Yeah, no, I don't know that.
I've got the news report on my computer.
Okay. I didn't think it was quite there.
Well, their press office said that.
Okay, well, yes. You need to look at the papers, but anyway. Yes. No, I actually saw you first, so.
Is the calculation, could you reinterpret the calculation which you said as being that there is entanglement between the mirror motional state and the state of the light, or is it not that simple?
Well, in LIGO, one has to, there you have two mirrors, and those two mirrors are moving, and you're looking at the difference between them. So they have to also maintain their coherence over those two mirrors so that the difference between them acts properly. So there is I think one can make an argument that there is a coherence between the two mirrors as well in order for LIGO to work. But I haven't looked into that deeply enough to be terribly confident.
I think Ari had a question.
So it seems to me, at the moment you assume that there are no internal modes of
That works. I'm sorry,
So it seems to me, at the moment you assume that there are no internal modes of excitation for the mirror at the frequencies between omega and omega plus mu. It became quantum mechanical because it's coherent and there's no way to change its state, but to have the state changed
Right.
by light scattering.
Well, remember that omega plus mu is 10 to the 15 hertz, and a 40 kilogram mirror hit by a force at 10 to the 15 hertz simply doesn't move whatsoever.
So it has no imaginary part to its response function. It is not excited anywhere in this.
I mean, at those frequencies, I mean, even the acoustic oscillations in that mirror at that kind of frequency are completely negligible.
So once that is the case, then it seems to me it must be a quantum object because nothing decoheres it. So
Well, I mean, it could be a classical object from word go. Okay, it could be that as Bohr says, when you got some big thing sitting on your table, your measuring apparatus, that's classical. Okay, and if you have a little atom, that's quantum.
yeah.
And many people have, Tony Leggett, who's certainly somebody who understands quantum mechanics, modern quantum mechanics extremely well, for many years was arguing that these superconductors, with 10 to the 22 pairs, etc., was in the regime in which it would act classically, not quantum mechanically. that there was a limit to quantum operations set by something or other. And so this is an attempt to drive a spike into the ideas that anything in the world is operating in a distinctly different manner from the quantum matter. Of course, it doesn't prove that. All it does is prove that these particular silicon dioxide lumps of glass are behaving quantum mechanically. But, you know, mostly our physics doesn't operate on such particulars. They're generic.
Can I ask another question?
Sure.
Sure. Is there any similarity between these noise cancellation techniques that you explained and the noise cancellation technique in headphones?
In your headphones?
Yeah.
Not really, because this is, I mean, in your headphones, what happens is that there's a little microphone that listens to the noise that's going into your ear. It knows, it's linked also to your little radio or whatever, your receiver, so it knows what noise should be going into your ear, and it simply goes ahead and cancels out those frequencies that differ between the two. So it de-amplifies all the noise that's different between what should be going in and what actually is going into your ear.
Here we don't know what should.
And so it's actually reacting to what's going on in the environment. Here you can actually calculate how the response of the system is. You know, how the system will respond. You, of course, don't know what the quantum operators are because they will take whatever values they want. But by feeding in the right quantum state, you can make sure that those operators operating on that state don't give you any signal. So it can all be planned beforehand. So you've got the immense advantage that, in a sense, you know what the noise source here is and what its characteristics are, and you can therefore cancel it out.
It's not a real time.
Instead of doing it by feedback as they do in the headphones.
All right, let's thank Phil again.